Hello everyone, today we will discuss reductive elimination. In the last class we have completed oxidative addition and we have seen three different mechanisms of oxidative addition. Today's class we will discuss reductive elimination, also we will discuss as RE. Now reductive elimination is exactly the opposite of oxidative addition. It's like counting 1 to 100, 1, 2, 3, 4 and 98, 99, 900, and then reductive elimination will be, if that's the forward direction is oxidative addition, reductive elimination will be counting back from 100, 99, 98, 97, 96, 95, so on to 1. So, technically there is really not much new things, but again, reversing something is not that easy. That's why we need to discuss, and the principle specifically we would like to focus. We'll discuss reductive elimination very briefly. Once again, whatever you have learned in oxidative addition, if you can reverse it, okay, it's kind of microscopic reversibility of oxidative addition. Okay, let's look at reductive elimination. So, reductive elimination will be starting from a ligand metal complex having A and B component. This is the species you get after oxidative addition into A and B, right? So the reductive elimination will be on the forward sense to give you ln M and A, B. You can understand that the backward direction of these would be oxidative addition. So ligand metal complex interacting with A and B to give you ligand metal AB by oxidative addition. By reductive elimination RE, we are looking at that oxidatively added intermediate, or an intermediate where a possibility of a bond formation between A and B can be looked into. Starting from that complex, we are going to generate ligand metal species as well as A and B. So the new bond formation between A and B, that is the reductive elimination from a organometallic intermediate. One of the requirements for this reductive elimination simply is A and B must be cis to each other, must be cis prior to reductive elimination for concerted reaction. You have seen in oxidative addition we have three different mechanism: concerted, radical and your SN2 mechanism. But over here you need to have A and B in cis conformation before they want to reductively eliminate. Now also you would understand the change in oxidation state from ligand metal AB is going to be -2, right? If you are starting the electron count for a ligand metal AB complex as 18 electron, after oxidative addition that will be 16 electron. Sorry, after reductive elimination it will be 16 electron. In the oxidative addition, you have seen if a 16 electron species is undergoing oxidative addition, it is giving you 18 electron. So for oxidative addition, 16 goes to 18, and for reductive elimination, 18 goes to 16. Now, if you have seen very carefully, the effect of ligand on the metal complex are paramount, are very, very important in oxidative addition. Similarly, for reductive elimination, effect of ligand will be crucial. For oxidative addition, you have seen smaller the ligand and electron richness of the ligand will also favor oxidative addition. Small ligand, electron rich ligand will favor oxidative addition. Now, since it's a reversal of oxidative addition, reductive elimination will be supported by a ligand which is bulky, which is very big, That means it will not allow A and B to stay with the metal complex very strongly. So the big ligand will enhance or facilitate the removal of AB. So steric bulk of the ligand will be good for reductive elimination. Of course, another thing will be electron deficiency. If ligand is electron deficient, then a higher oxidation state, such as in 18 electron cases, higher oxidation state will not be favorable. Therefore, it will undergo reductive elimination to give you the product. Once again, for oxidative addition, you need a small ligand and electron rich ligand. For reductive elimination, you need a big ligand or so-called sterically crowded ligand and electron deficient ligand to make it more facile. So that's the kind of direct relation. So let's write down that fact. Reductive elimination RE accelerated by number 1, as we discussed, reduction of electron density at M, means metal, and the bulkier ligand. So, of course, as we also have tried to discuss, reductive elimination usually a concerted process. That means it's a metal A and B are interacting together. It's almost it's a sigma bond metathesis type of reaction you would see. So it is usually a concerted process, 3-centered reaction you can imagine. So let's try to write down the transition state for this. Usually a concerted process. Therefore, if you start with M, A and B complex, okay, from here you will have a transition state where these 3 components are interacting, and finally you will have M, A, B formation. Fine. So it's a concerted process, and therefore you will have interaction between M, A and B. Therefore, finally you will get M and AB back. Now, in oxidative addition, we have seen, depending on the mechanism, the stereochemistry can be influenced. If it is a concerted oxidative addition, we have seen retention of configuration of Rx or AB if there is any chiral center present. So if you start with R isomer of a species, okay, then you will not see the inversion if a chiral center will remain basically intact, right, for concerted one. For SN2, as you see, as all the SN2 reaction, you will have the inversion of the configuration at the AB or Rx, whatever we were discussing. If they are having a chiral center, then we will get an inversion. But for radical reaction, of course, you have seen that it is the racemization of the chiral center. Okay, so concerted oxidative addition gives you the retention, and your SN2 reaction gives you inversion, and radical mechanism gives you the racemization of the chiral center. Now, for reductive elimination, since we have seen it's usually a concerted mechanism, so most often or almost nearly always we get retention of configuration. So retention of configuration is for reductive elimination, and cis configuration is usually necessary for reductive elimination. Let me draw with an example. Retention of configuration at A and B, right. So we would like to discuss one of the example. Very simply, if you have a palladium complex where these two groups are there. Now, to have a compound like this, you must be able to identify A and B very easily. This is A, let's say, and this is B. So, there will be bond formation between A and B to form AB species, right. After reductive elimination, what you will get, of course, you see that these two species are A and B are cis to each other. Overall, at the end, you will get this retention of configuration, right. So, the stereochemistry is retained at this point, and in this case ligand equal triphenyl phosphine. Okay. So, what you have seen right now is one example of the palladium. This is a palladium 2 oxidation state. This palladium is having 2 plus oxidation state. A and B are getting reductively eliminated to give you the product with retention of configuration. Of course, another thing is, it's not very common, but another thing is we can make the reductive elimination facile by adding exogenous ligand. From outside you can add and show that this ligand will be effective for promoting reductive elimination. So, if you have a ligand metal complex and reductive elimination is not facile, the technique here sometime could be is simply add another ligand, okay, exogenous ligand from outside, which will take out the electron density from the metal center. Therefore, in principle, you can promote reductive elimination little bit faster than before. Of course, in every cases you are not going to get reductive elimination faster. You have to in order to promote the reductive elimination by adding another ligand from outside, you have to ensure that ligand, outside ligand is interacting with the metal complex, with the metal, and then taking out the electron density from the metal. Of course, it is not going to be feasible always, but sometime it is possible. Sometime it is possible to take out the electron density from the metal by adding ligand. Again, you must remember that it is, although in principle generalized technique, but you need to have perfect choice of the ligand, and without changing way too much of other things at the metal center, the ligand should be able to coordinate with the metal and should be able to take out the electron density from the metal. Therefore, almost like pi back donation type of thing. If that is feasible, then you may have a possibility, actually then you will have a possibility that reductive elimination can be made faster. Okay, let's discuss with one of the example. So, reductive elimination, okay, can be accelerated by addition of appropriate ligand. Okay, that's what we are trying to discuss right now. The example you need to have for these cases, or one of the seminal example, is the complex with bipyridine. You know it's also known as BP. Okay, this is bipyridine. It will coordinate with any metal center in a 5-member chelating fashion. In this case, nickel, and we have 2 methyl. Of course, this is A, this is B. So, we are trying to promote reductive elimination so that carbon-carbon bond between these 2 methyl group is formed. Usually, if we try to do this reaction, we will see it's a slower reaction. Of course, you can try to heat it up, you can usually promote it faster, but still it's a slower reaction. Now, what you can do is, in this particular case, you can get the same product formation in a very fast manner or relatively faster manner if you add this anhydride to it. Okay. So of course, again, this happened to be the perfect choice in this case. It's a tetra coordinated nickel, and then what one would expect that this nickel will coordinate with this anhydride in the fashion, and here is your bipyridine and methyl. Since nickel is coordinating with the with this anhydride in this fashion, it will be able to take out the electron from the nickel center, and therefore this will act as an electron withdrawing ligand, and you will be able to promote reductive elimination between these A and B relatively faster. Okay. And then thereby it's demonstrating that reductive elimination can be accelerated by choice of a suitable ligand. If you choose a suitable ligand, you have an opportunity to promote reductive elimination faster. Once again, reductive elimination required bulkier ligand as well as electron deficient ligand. So you need to create an atmosphere around the metal center such as it feels like it is not electron rich, and it feels like it is sterically crowded. So if you see, this oxidative addition and reductive elimination are kind of not mixing well with each other, right? They are kind of, on the two sides. So that's why often you see the problem that if in one reaction, let's say in one catalytic cycle, you need oxidative addition as well as reductive elimination, then the choice of ligand is very crucial, because oxidative addition will require rich ligand, electron rich ligand, and smaller ligand preferably, but reductive elimination will need bulkier ligand and the electron deficient ligand. So in one reaction, in the same reaction, if you want oxidative addition and reductive elimination to be facile, it is kind of really tricky thing to deal with, and this is where extremely important factor for these organometallic species is the ligand design. How do you design a ligand when it is electron rich in one hand, at the same time electron deficient on the other hand? How do you design a ligand which is bulky in one hand as well as less sterically demanding on the other hand? This is like almost classic, and people have contributed, and famous faculties from different institutes has contributed enormously to solve the dilemma. But of course, now the understanding of the literature is such a conundrum, such a mutually exclusive things can indeed be promoted. Okay. Now, of course, another thing we would like to discuss is some more example, or the ligand effect, let's say. So more electron withdrawing ligand we want to discuss little more. So let's take an example, since we are discussing palladium little bit, or not really, we are just taking some example. Let's say this is a compound. Of course, what we are trying to see? We are trying to see the reductive elimination between A and B. What you are expecting? You are expecting to get methyl plus, of course, the remaining part PdL2. If it was in +2 oxidation state, it will be 0, right? This is the thing you should be very quick in doing. So palladium 2 goes to palladium 0 for reductive elimination, palladium 0 goes to palladium 2 for oxidative addition, right? Now, in this case, if you have a ligand, imagine this ligand, if you have a ligand which is PPH3, and if you have another ligand which is PPH2ME, what do you expect the relative rate to be between these two ligands? Which one will be faster? Triphenyl phosphine will be faster, or diphenyl methyl phosphine will be faster? Okay. just let me give you the value. Triphenyl phosphine is faster, this is slower. Why is that? Simply, first of all, triphenyl phosphine is bulkier and this diphenyl methyl phosphine is less bulky. So, triphenyl phosphine will promote reductive elimination faster. That is fine. Number 2, of course, is this is also going to be less electron rich. This is going to be more electron rich, right? This is more electron rich compared to this. So, you need a bulkier ligand as well as electron deficient ligand for reductive elimination. You see that's why the relative rate is varying like 11 versus 1. In other case, for example, if you have PF3 versus if you have, let's say, P-alkyl 3, trifluorophosphane versus trialkyl phosphane, okay, which one will be giving you faster reductive elimination, whether this alkyl group will promote the faster one or the fluoride will give the faster one. If you apply the same principle, once again, you will see that, of course, PF3 is electron deficient as well as smaller in size, or mostly electron deficient, okay, and this is it depending on the alkyl group. Of course, you will have different steric bulk, but this is usually, of course, very much electron rich. In this case, since this is very electron deficient, you will get faster reaction rate. Overall, you will get slower reaction rate. Okay. So, if you have a sigma donor, then you have low or slower reaction rate, and if you have a pi acceptor, you have very high reaction rate. Okay. So, for example, carbon monoxide will promote the reductive elimination very faster. We will close the discussion of reductive elimination here. What we have learned so far today is reductive elimination is almost the microscopic reversible fact of the oxidative addition. Whatever promotes reductive elimination will not be the same factor for the oxidative addition. For oxidative addition, we need smaller ligand, electron rich ligand. For reductive elimination, we need bigger ligand and electron deficient ligand. Of course, they are kind of non-mixing with each other, therefore promoting both oxidative addition and reductive elimination in same reaction is always going to be problematic. This is where ligand design has to be perfected. We will look at that in a later class, and we have also discussed quite a few examples and shown that you can sometime be able to add a ligand from outside, and thereby you will create an electron deficient metal center which can lead to a faster reductive elimination. With that, we conclude today's session, and that is on reductive elimination. Next class, we will discuss migratory insertion and elimination reaction. So, we will also discuss in that, we will discuss alpha migratory insertion and alpha migratory elimination, and also beta migratory insertion and beta migratory elimination. So, that is for the next class. Okay. Thank you all.